Hello, my name is Randy Pitts, and my paper is Quasi-Dominators in Random Selection in Mutation Testing. This is a really large domain, too much to cover in a short period of time, especially for an audience not made up of software testing researchers. So my goal is going to be to cover it at a high level and hopefully pique your interest. If you are curious, the paper's there with more details, and of course with all the references to all the other great work it's based on. So what is mutation testing? Probably the quickest way to do this is to demonstrate it with an example, and I'm taking this straight from the paper. If we had a simple statement like this, we could create mutations or mutated versions of it for designed to elicit good tests or to test the efficacy of an existing unit test set. There's different types of mutants there. There's one type we call redundant. These are mutants that are killed by the same test, and that's a bit of an oversimplification, but the premise is that if a test kills lots of mutants, it's sufficient to have one of those mutants because that mutant would elicit the tests. And here's an example of redundant mutants. For example, if the original operator was replaced by the OR operator, bitwise OR, and the logical OR, well, with Boolean operands, these two behave the same. Another type is the equivalent mutant, what's historically been called the equivalent mutant. These are semantically identical to the original code, and for that reason, they are not killable. And here's an example of an equivalent mutant. Similar to the OR, the bitwise and logical OR, the bitwise and logical AND operators also behave the same with Boolean operands. So this first mutant would behave identically to the original source code, and therefore the mutant would not be detectable by unit tests. Other kind of nuisance mutants are mutants that might create endless loops or be uncompilable. But the mutation testing tools are pretty good about catching these kind of mutants. There's quite a few types of transformations or mutations that can be affected on source code. For example, these conditional operator could be replaced with another conditional operator. The equality operator, the not equality operator. You can negate one operand or the other. You could negate the entire expression and so on, delete part of the expression, replace it with literal true and false values. Anyway, the thrust of that, though, is that we create very high numbers of mutations for just a small piece of code here. And the subjects that are studied or incorporated within this paper create a total of 11,000, almost 12,000 mutants. But it's also real-world code. These come from the Java Lang package, and I've taken them from the Defects4J suite of tests and code. These bundle defects and known defects with their solutions and fixed code, defective code, and the original unit tests from the developers. What makes these 15 stand out is that where the original developer tests fell short of achieving a mutation score of 100, in other words, killing all the mutants, tests have been added to them to reach that point. So these are known to be mutation adequate, and that's significant. The traditional metric in mutation testing is the mutation score, and that's calculated very simply by dividing the number of mutants killed by the number of mutants that there are. And in the case where equivalent mutants are known, in other words, the unkillable mutants, the mutation score is derived by dividing the killed mutants by the mutants that are known to be killable. All right, let's talk about the strength of random selection. Back to the notion of mutation score, we can sample take the mutation score early on. Let's say on the x-axis we've got the amount or the number of mutants that the tester has evaluated, in this case 2% of the total. Traditionally, it rises very quickly and then sort of plateaus, and there's a diminishing returns associated with more work, which kind of disincentivize the testers to keep going. We can sample it essentially continuously and get a continuous mean mutation score. Now, because everything we're working with is mutation adequate, they all reach this maximum score of 100. So we're really concerned more with the effort expended to get there. In this case, or this example, the tester assessed 21% of all the mutants before they managed to kill all the mutants. And you might think, well, that's not even a quarter of the mutants, and that's because of redundancy, again, where this score rises rapidly because tests tend to kill a large swaths of mutants, and then the subsequent tests need to kill the residual mutants. Our real goal in all of this work is to reduce the effort it takes to get to that score of 100. Right? We want to get there, but we'd like to get there faster. This gives us a target region. If we're going to improve performance, then this curve needs to move up into that green area. Common sense tells us that we can't have 0 tests and hit 100% killed. So we're going, some portion of this region is effectively impossible to reach. And we have a de facto maximum or ceiling, if you will, in the form of what are called dominator mutants. So that shrinks the region that's accessible effectively to relatively small. We'd like to shift the lower line into the green zone. And just as a reminder, both test sets reach the score of 100, but we want to reduce the effort it takes to get there. So now you're probably asking, well, what is a dominator mutant? And to understand that, you need to understand another principle we call subsumption. And basically what that means is that if every test that kills one mutant also kills another mutant, the one mutant subsumes the other mutant. And the takeaway from that is it's sufficient to target the subsuming mutant, because if we kill it, we know we kill the other. And the mutants, we can graph this in terms of hierarchy, and the mutants that are at the top of the hierarchy are called dominators because they subsume, but they are not subsumed themselves, except by other dominators. So if our goal is to reduce the effort it takes to maximize the performance, and we know that dominator mutants are effectively the ceiling or the maximum performance, that we wonder then, what do dominator mutants benefit from, or where does their performance advantage come from? And we know that they're imbued with all the subsumption relationships, and consequently the equivalent mutants as well. So to basically to kill all the killable mutants leaves the non-killable mutants exposed and known. So we were curious if what would happen if we randomly selected from only killable mutants. In other words, if we could also avoid the non-killable mutants the same way the dominator mutants do. And it turns out that we have enough data to run those sort of simulations. And it turns out that random sampling from non-equivalent mutants, in other words, the killable ones only, performs almost exactly as dominator mutants do. We can zoom in a little bit here and see that there's a little disparity here. In fact, the non-equivalent ones actually tend to marginally outperform the dominators most of the way through. But for this part of the graph really doesn't matter. You know, again, we're aiming to get to 100, but to do it faster. And from that perspective, the dominators, although the non-equivalents outperform them very consistently, the dominators always finish slightly ahead of the non-equivalent mutants. But nevertheless, the non-equivalent mutants perform relatively well. All right, let's move on to mutant subsumption graphs. So as I mentioned earlier, it's possible to graph the subsumption relationships. And here's an example of one. This is one not the largest subject. I think it's Lang 1 with about 1,700 mutants. But it's this macro view of it lets us see some of the properties that are common amongst the graphs. First of all, they're disjoint and semi-disjoint. You can see that here. There's a separation there and here, and there's a lot of sort of onesie, twosie, smaller bits over here. That's disjoint, but again, semi-disjoint, we see an obvious piece here where this massive node is connecting these two larger ones together. And there's a lot of that sort of hidden or obfuscated in the detail here that, again, we can't see it. Same with them being directed acyclic graphs. We'll see that at the micro level here in a minute, but they tend to be wider than they are deep. You see that here. And there are large numbers of indistinguished mutant groups. This is a fancy way to say there are multiple mutants in a node or in a group, and you can sort of see that here, but again, we'll see it in the drill down in a minute. Here's one that's more accessible visually because it's smaller. This is Lang 55, but it does exhibit some of the same characteristics. More indistinguished groups in nodes than there are distinguished or individual mutants in nodes. It's wider than it is deep. And then here you can see the directed graph. Mutants are noted in nodes in the graph. All mutants in a given node are killed by the same set of tests. Subsumption relationships are indicated by the outbound arcs from nodes. So in other words, these mutants, 116, 117, 132, all subsume mutant number 27. Now it's important to remember too that they subsume each other as well, because a test that kills one kills the others. We've got dominator mutants. They're generally easy to recognize because they're at the top of the graph, if the graph is neatly oriented. And there's a convention, double lines on those nodes. Indistinguished nodes, again, are these that have more than one mutant in them, and they don't have to be dominators. They can be non-dominators as well. Okay, so let's talk about subsumption and dominator behavior. All right, so here we are back at our subsumption graph. Again, this is Lang 55. It's comprised of 178 mutants, 40 of which are unkillable or equivalent. So there's 133 killable mutants here. But let's say we were randomly selecting a mutant to kill, and knowing what we know about subsumption, probably the worst case scenario would be to draw something from the bottom of the graph here, right? Because if we killed something up at the top, we're going to kill those and also do some subsuming, which we'll see in a second. But again, worst possible scenario would be to draw one of these 8 mutants and target it. Maybe the next worst thing would be maybe draw 27, write a test to kill it, and it subsumes these 8 as well, so there'd be 9 mutants killed. But I want to demonstrate something real quick here, and that is if we, even with worst case scenarios, when those are killed and gone, the remaining mutants, the remaining graph in terms of a target is changed dramatically. No matter what's killed, the bits that vanish from the bottom increase the probability of anything above it being selected, right? So we've knocked 9 off the bottom out of 133. It's not quite 10%, maybe, I don't know, 7% give or take. But the probability of selecting the rest increases. Let's take another look at that. So somewhere in the middle, we draw 80 or 82, and we write a test to kill them, and naturally that test kills everything that's subsumed by that node or the mutants in the node. Now, obviously, it's better to draw something higher up the subsumption hierarchy, but now keep in mind this is random, so there's some, we say it's better, but we're not necessarily aiming higher. But If you could, you'd say, well, why not just go right up to the top and grab a dominator and then subsume all those? But of course, it's more than just that line. It's everything that's subsumed by a distinguished node. And you can see with one test that a fairly large swath of mutants are killed. Alternatively, go back to these three that we targeted a minute ago and realize that those are subsumed by other routes as well. This dominator node here subsumes quite a bit, kind of mixed all around the graph. But another thing to note is, for example, we pretended we drew this one randomly a minute ago, but note that because this node has 3 mutants in it, it's 3 times as likely to be selected as this one. There's 1 mutant in this node and there's 3 in this one. And of course there's others with even more, 5 here and 8 here, 7 here. So although things are random, there are probabilities associated with what is selected. This is probably the strongest. If you measure strength in terms of how many mutants are killed, drawing one of these 8 and killing it results in the largest single swath on the whole graph being subsumed. And you can see it's quite a bit. In fact, this is it's 50-something mutants that are killed, so it's actually more than 1/3 of the entire graph that can be killed by a single test. But being a dominator mutant does not guarantee large numbers. For example, mutant 106 or this node 106 only results in 5 mutants being killed if you were to draw this one randomly, because this is a leaf node here. This is the only leaf node in the graph other than this one because it's a relatively simple graph. It's a dominator, but it only results in a marginal increase of score of 5 mutants in the total mix. Along the lines of least performing or the worst case scenarios, if we pick the least 4 effective tests, and let me backpedal and expand the simulation here and say, let's say we drew a mutant out of each of these 4 nodes. So we draw a node, we draw a mutant, and then we write a test to kill it. Again, draw a mutant, write a test to kill it, and so on. These are the 4 least effective. And you can see there's a swath of mutants killed, but even the 4 of them don't total up as much as having killed that one would have. And along those lines, if we look at the most effective 4 tests, in other words, we simulate drawing a mutant from these 4 dominator mutants and writing a test to kill it, you can see that very nearly the whole graph has been wiped out at this point. You see a pattern of the remaining dominators and a handful, a smattering of remaining mutants. And that is the pattern that tends to come out most frequently, except let's say we do 4 average ones. You get 4 dominators, and again, a large swath of the mutants are killed off almost immediately. There's a little shift over here, a few more, but what you see again is this pattern of dominators remaining and the low-hanging fruit being killed off relatively quickly. Let's take another look at this single worst performing test, or least performing mutant. This mutant number 106 and the test it elicits. It only results in 5 mutants being killed. It's possible for this to perform even worse if what better performance means is killing more mutants. And that's if it were the last mutant left in the graph to be killed. Notice that the mutants or nodes that it subsumes are also subsumed by other nodes, so it's not uniquely subsumed here. So in this scenario, rather than killing 5 mutants, this would only result in a marginal gain of 1 mutant in the mutation score. But is it any less important than these other mutants? I would say no, because in order to kill all the mutants, you've got to kill all the dominators. And the corollary to that is you can kill just the dominators or target them and end up killing everything, right? So each of these nodes is equally important. And every mutant is important, but again, if you can target these, you kill all the non-dominator mutants as well. Well, that begs the question then, why not just target dominator mutants? It's because in practicality, dominators can't be identified until all the mutants are killed, because all the mutants need to be killed to determine what the subsumption relationships are. And dominators are relevant to a given test set and will differ depending on how the tests are written. All right, so that brings us to quasi-dominators. Let's go back and review our least effective 4 tests and note that even though they're the least effective out of the entire suite of tests written for Lang 55, 3 out of 4 of these result in killing dominators. There's this 4th one here that kills a non-dominator node and subsumes some stuff. And again, because of the behavior, that increases the probability of others. But some of these are not even relying on that phenomena. They are directly killing dominator mutants, 3 out of 4. And dominators make up 40% approximately on average across all of our subjects, and non-dominators are 60%. You can see that graphed here, 39.7 to be exact, and it is an average, so there are higher observations and there are a few low ones. But when you think about it from that perspective, if you only have a 40% probability of randomly drawing a dominator, why then do we get this dominator-like performance? I've got a graph that annotates the subsumption graph with the tests that kill each node. For example, this node's killed by test 2, test 14, and so on. But it's small and hard to read, so I'm going to simply superimpose the germane parts onto the regular graph we've been looking at, and I'm going to leave the others in red so that the new ones stand out. So if we look at these 2 dominator nodes, 11 with mutants 11 and 22 and mutants 12 and 14, we can see that the first is killed by test number 7 and the other is killed by test 16. Now if we look at the mutants the other nodes that are dominated here, this node is dominated by both. They all also dominate others, so this one here and this one's going that way somewhere. But what they are participate in jointly is these paths here. And notice that the subsumed node is killed by the exact same 2 tests that kill the subsuming nodes, or the dominators that subsume it. But more importantly, notice that it's not killed by anything else. It's only killed by dominator killing tests. And what we can infer from that is if we were to draw mutant number 10, we're likely to write a test that looks and feels like this one or this one, and none, and in this case, none other. So for all intents and purposes, if we draw mutant number 10, it's going to behave like a dominator. We don't know which one until we write the test. It may elicit this test or one like it. It may elicit this test or one like it. But in either case, it's going to result in a dominator being killed and everything else that dominator kills being subsumed as well. So even though, for example, mutant number 10 is not a dominator, it looks and behaves like one, hence the name quasi-dominator. And it turns out there are quite a few of these. I've marked them in gray here. All the gray nodes are quasi-dominators. So in addition to the 40% dominators at the top, there are these others that extend the reach of dominators, and it turns out across all subjects the average is roughly 30%. So it increases the reach of dominator behavior to 70% of all the mutants. And that's graphed here, 72%. The graph shows dominators, proper dominators and quasi-dominators, extending them, but you can see now roughly 60, in the 60 plus arena, and mathematically 72% of all killable mutants are dominators or quasi-dominators. So you can see a much higher probability, basically nearly 3 and 4, which kind of maps onto our worst case scenario. There's that probability of drawing a dominator or dominator-like mutant to kill. And that goes a long way to explaining why the random selection of killable mutants, only killable mutants, performs effectively as well as dominators do. I've done a little more research since submitting this paper, and it's going to be published soon at the Mutation 22 workshop. But it indicates that of all the mutants that are not dominators or quasi-dominators, 74% of the tests that kill them are still dominator killing tests. So in other words, 70% of mutants are either dominators or behave like dominators, and of the 30% that are not, they are still fairly likely to elicit a dominator killing test and behave like a dominator. Again, even non-dominator mutants are likely to elicit dominator killing tests. All right, so back on track here. We look at the probability of the mutant types being selected randomly for the duration of testing, and this one's shorter than the 21% because it doesn't have equivalent mutants in it. But dominators are always the most probable to be selected randomly. You can see here we've got distinguished dominators, indistinguished, and these are the proper traditional dominators, quasi-dominators, and then other killable mutants. So you look at the other killable mutants are down here at the bottom. So at virtually every point through the process of testing, dominators or quasi-dominators are the most likely to be selected. And regardless of what's selected, the rest plummet rapidly because of that low-hanging fruit, the funneling effect of everything that's subsumed gets killed very rapidly. So killing mutants almost seems like a can't-miss proposition. The problem is that there are relatively large numbers of unkillable mutants. Remember, in line 55, 40 of the 178 mutants are not killable. So roughly a quarter in that case, but 40 out of the 133. Each unkillable mutant requires evaluation. There's no subsumption or redundancy. Each one has to be evaluated. They take a lot of time. And you can see here in this graph that's been augmented with equivalent mutants, and the dominators of all types are aggregated together. We've got the other killable mutants, but they exhibit the same behavior. The other killable mutants plummet quickly, as do the dominators of all types. And what replaces them in terms of probability are the equivalent mutants. And I've augmented this graph with mutation score, and you can see here by the 5% mark, mutation score typically already passing 90%, the probability of killable or dominator types dropping rapidly, and the probability of equivalent mutants quickly approaching double that probability. So testers tend to feel good about the score, they start feeling the pain of equivalent mutants, and they decide that they're done. So we've got some simplifying assumptions in play throughout this. The subsumption relationships, including dominators, are relative to a specific set of tests. Tester 1 writes test, or tester 2. The relationships are going to change slightly. Or when randomly selecting an existing test to simulate killing a randomly selected mutant, we assume that a future tester will write a similar test. and they may not write that similar test, but whatever tests they write, similar relationships are going to exist for that set of tests. So the phenomena we observe, the behavior we observe is going to exist regardless. So in conclusion, dominators and non-dominators empower random selection, and equivalent mutants remain a significant problem, if not the problem for mutation testers.
Thank you very much. Sounds really interesting. I have a few questions for you. First of all, I have to say that in my practical experience of being a programmer, I know that very often people don't use mutation testing. They just do unit testing, and they rarely apply this mutation for a number of reasons. Reason number one is the speed, the amount of time it requires to run the mutation testing for the large data set. So it seems that your approach can help them reduce somehow the amount of efforts they spend, right?
Yeah, there's your points. You're right on the mark that mutation testing is it's resource intensive. It takes a lot of manpower. It's resource intensive on the machines. It's also intensive on the people doing the work. So that's another factor in why people stop early or even don't embrace it at all. But there are a lot of efforts underway to sort of make fractional or partial testing. I know I don't have firsthand knowledge, but there's some papers out there from Google. Practitioners at Google are adopting mutation testing, but they don't embrace it sort of globally. It's more fractional, and that's where actually the idea of drawing mutants one at a time randomly sort of comes from, is just doing a subset of all the mutants.
Is it possible, or may it be possible, to integrate your approach into one of the testing frameworks? Let's say I have my code, I run mutation testing, it shows me all the problems I have, which mutants I still have, which are not killable, and then they show me the tests, and then they tell me that, draw the graph actually, which you demonstrated, and shows me which mutants I should pay attention first. Who are the dominators, who are the quasi-dominators?
Yeah, there's a lot packed into your question. It is definitely, in terms of configuration management and deployment, it's definitely possible to integrate mutation testing with ANT and other tools. And sorry, I forgot the second part. Graphs. I'm not aware of tools that draw graphs for you, but they do tell you which mutants remain unkilled. The dominator designation, I don't think, is integrated into tools, because you really need to exhaustively kill everything to determine the subsumption relationships before you know what the dominators are. There's research underway to try to pre-identify dominator mutants or mutants that could potentially be dominators. But of course, that's still even dependent on the ultimate test set. So I'm more focused moving forward on how to avoid the equivalent mutants, because that's a static relationship. If a mutant is unkillable, it's unkillable. It doesn't matter who writes the tests. So that, and what my research is showing is that randomly drawing from the killable mutants only is effectively as efficient as drawing dominators. So you don't need to have that foreknowledge of the relationships, but it would help if you had the foreknowledge of the what's equivalent or not. Does that make sense?
Yeah, it does. Yeah, definitely. So it seems like you're far ahead from the what we have in the industry, because people are not using mutation testing a lot, but you're suggesting us to do smart mutation testing, which is
right. And again, I don't have firsthand experience, but I think Google is doing just that. From some of the papers coming out of Google, they are doing partial.
How much time did you spend on this project? I'm interested. It looks like a long project, a long running one.
When you asked the other two folks the same question, I started thinking, well, how would I answer that? I've been working on this overarching area for about 3 years. I spent I would say several hundred hours, right, roughly half time, 4 hours a day for about 6 months, just analyzing the subjects and and identifying the mutants that the developer test left unkilled. I'd analyze each one and say, could I kill it or not? And I cut that gap about in half. But like I said, I think they're mutation adequate now. So that was very resource intensive. And again, it's another reason why the typical developers don't take it to that threshold. But having that, that was part of another project to get ground truth for that principle for doing machine learning, which is also going on in parallel. So I've made these sort of observations as part of ongoing efforts that have lasted about 3 years. But I won't say this didn't take 3 years. These were things that I've been noticing and thoughts coalescing, and I dig in a little bit. So it's sort of a part-time, long-term effort, if that makes sense.
Yeah, it does. Okay, then I thank you very much for considering us, our conference, for your paper, and I hope to see you next year.
Yeah, I'm pleased to be here. Maybe next year in person.
Oh yeah, that would be great.
Yeah. Okay. Take care.
All right, then thanks everybody who joined us today, who submitted papers, the authors, the program committee, everybody. I am closing the conference. I see you everybody next year. Again, consider submitting to us. At least, even if your paper is rejected, at least you will get a very professional feedback from the program committee who works for you to help you improve your research. Bye, everybody.